Welcome and thank you for joining me in this lesson. Today, we'll be exploring the factor theorem and learning how it can be used to factor polynomial functions of degree 2 or higher. You may remember that in prior grades when you learned how to factor quadratic polynomials. Now in grade 12, we'll extend those same ideas to factor polynomial functions of degree 3 and higher. By the end of this lesson, you'll be able to use the factor theorem to express polynomial functions in completely factored form. Before we begin, let's quickly review the remainder theorem. Recall that when a polynomial f of x is divided by a divisor of the form x minus b, the remainder will equal the value of the polynomial at b. And when a polynomial f of x is divided by ax minus b, then the remainder would be equal to the value of the polynomial at b over a. An easier way to figure out these numbers is by finding out the zeros of each divisor. Now, let's connect this idea to ordinary numbers. Suppose that we divide number 6 by 2. The answer will be 3, remainder 0. We say that 6 is equal to 2 times 3, which means that numbers 2 and 3 are factors of 6. If we were to divide number 7 by the same number 2, we get the same answer, 3, but this time we get a remainder of 1 in addition. So we're going to say that 7 equals 2 times 3 plus 1. In this case, we're going to say that 2 and 3 are not factors of 7, and that is because we have a number added to the end of it, and that is the remainder, and it is not equal to 0. It's different than 0. So in general, we're going to say that whenever a division results in a remainder of 0, then this divisor will be a factor, and this quotient will also be a factor of the dividend. Now, the same idea will apply to polynomial expressions. It states that if the remainder, when a polynomial is divided by some linear expression, is 0, then that linear expression is a factor of the polynomial. Now, this would lead us to the factor theorem, which is really just a special case of the remainder theorem. The factor theorem states that a polynomial f of x has x minus b as a factor if and only if the value of the function at b is 0, which means that the remainder would be equal to 0 when f of x is divided by x minus b. A polynomial of f of x has ax minus b as a factor if and only if f at b over a is 0, which means that the remainder would be equal to 0 when f of x is divided by ax minus b. Now, how does this work? How can we determine which divisors might be factors of a polynomial? Before applying this idea to polynomial expressions, let's review a concept that we are already familiar with. So we're looking at a polynomial function of degree 2, gx equals x squared plus 3x minus 10, and we'll factor. Now we're familiar with this process. You see that this is the easy trinomial to factor with a coefficient of 1, which means that we start off with writing two sets of brackets, and each set of brackets will start with the term x. And the term x multiplied by x is what gives us the first term in the polynomial function, x squared. Next, we have to figure out two numbers that have the sum of equal to 3 and a product of negative 10. We always start off with a product, and we think that since the product is negative, the two numbers must be opposite in sign. And since the sum is positive, it means that the bigger number is the positive. So I will start off with negative 1 times 10. Negative 1 times 10 doesn't have a sum of 3. So it means that these two numbers do not work. Next, we have negative 2 times 5. And as you can see, negative 2 plus 5 would satisfy the condition, obviously, of having a product -10, sum of 3. So we're going to write the numbers -2 and +5 in these two spots. And as you can see, the -2 and +5 are in charge of creating or recreating the constant term in the expanded polynomial. So we're going to say that the factored form of g of x here would be x minus 2 and x plus 5. So as you can see in this case, the values of b in these factors will be 2 and -5. And these two numbers will have to be factors of the constant term. So this idea can be extended to higher degree polynomial functions. So whenever we search for factors of a polynomial function, our focus will be in the constant term of the polynomial. So let's take a look at some examples. And before we do that, we're going to say that when x minus b is a factor of f of x, the values of b are the factors of the constant term. So we are summarizing what we were explaining. To determine all the factors of f of x that are in the form x minus b, we must use the possible factors of the constant term of f of x. So let's put these ideas to work. What we have in here is a cubic function, third degree polynomial, and we want to write it in factored form. So we're going to start searching for the factors, which should be in the form x minus b. So remember that f of x, since it is third degree, can have a maximum of 3 factors, and all the 3 factors will have to start with the term x. And this is where x to the power of 3 will come from. In order to figure out the constant terms in each factor, we use the constant term of the polynomial, because the product of these constant terms will give the number -15, the constant term in the big polynomial expression. So we're going to say that since constant term is -15, then the possible values of b, remember we treat these factors in the form x minus b, and that's why we use letter b in this case, would be the factors of 15 are plus or minus 1, plus or minus 3, plus or minus 5, and then plus or minus 15. Next, we have to search for the factors or values of b that can make the polynomial equal to 0. So for this, we're going to use that same equation of polynomial function, and we'll start with f of 1. f of 1 is easiest to find. You can do it mentally, because whenever you bring number 1 to any power, that is equal to 1. So you simply add the coefficients. So 1 plus 3 minus 13 minus 15. And what you get in here is 1 plus 3 is 4 minus 13 minus 15 will be a negative number. So 1 plus 3 minus 13 minus 15 would be equal to, I think, -24. So that's different than 0. So therefore, we're going to say that x minus 1 is not a factor. Next, we'll look into f of -1, and you want to try all these numbers one at a time and in correct order so that you won't mix them up and retry numbers that you have already tried. So we have -1 here to the power of 3, plus 3 times -1 squared, minus 13 times -1 minus 15. So this is -1 plus 3 plus 13 minus 15. So in this case, we're going to have a 16 positive and a 16 negative. So that equals 0, which means that x minus -1, or shall we say x plus 1, is a factor. Once you have discovered the first factor in a cubic function, you're almost done. So we are starting with dividing this polynomial by x plus 1. So synthetic division works pretty nicely. It's faster, and we are dealing with linear divisors. And we'll write -1 right here. So bring 1 down. 1 times -1 is 1. Add. 3 plus -1 is 2. 2 times -1 is -2. Add. -15. -15 times -1 is +15. Add again. And as you can see, the remainder is 0. If you don't get a remainder of 0, it means that we probably need to go back and check our answer, or maybe we made an error somewhere here. So far, we have obtained x plus 1 as one of the factors, and the other factor will be made of this quotient in here, which we are going to fill it in with the variables. So we have x squared plus 2x minus 15. And this will be f of x so far. This is not completely factored. We need to continue factoring further because we have to check this quadratic. But for the quadratic function, quadratic factor in here, we don't necessarily have to use this longer, more complicated method. We can simply factor it the way that we have done it in the past. So we have x plus 1. Set up 2 sets of brackets, start both of them with the term x, and then figure out 2 numbers that will multiply to a -15 and have a sum of 2. So product of -15 can be, again, -1 and 15. That doesn't equal +2. So we're going to search for the next factor. -2 doesn't fit in, but -3 does, and 5. And -3 and 5 also add to +2, which means that -3 and +5 will be our numbers here. And this is a factored form of this polynomial. Now, in case you're wondering, why do I have to factor polynomials? It is very important because this is how we're going to find the zeros of a polynomial function, and that would lead us to graphing polynomial functions with a lot more confidence. Now, the integral zero theorem will help us find the value of b when the leading coefficient is 1. So this method that we used right here is the one that connects the factor theorem with the integral remainder theorem. So these are the steps. So I wrote a summary of steps in here for you to use when you're practicing homework. But I would encourage you to write your own steps in your own words in the way that they make most sense to you. Now, in the next example, we're looking at a polynomial function where we have a coefficient different than 1. So how would that work? What happens if the leading coefficient is not 1? Well, when the leading coefficient isn't 1, possible linear factors are still easy to identify. But we will have to take into consideration also the coefficient of the leading term. So let's take a look again at an example that we are more familiar with. F of x equals 6x squared plus 17x plus 5. So when you factor this polynomial, you're going to set 2 sets of brackets. And what you want to have as a first term is an x term. If you multiply x by x, you get x squared. So what we need to get is 6x squared. So what that means is that we're going to have either 6 and 1 in here or 2 and 3. So I am going to try 2 and 3 and see if that works. It doesn't really matter where you put the numbers 2 and 3. And for the constant terms in here, we're going to use the factors of 5 like we did before. So I am going to use the 1 and the 5, and I'm going to place them as 1 in the first and 5 in the second factor. So 2x times 3x, 6x squared. 2x times 5 is 10x, plus 3x, 13x. So this cannot work. Now the reason I am using the trial method is because I know that 5 can only be written as a factor of 1 and 5. So I'm going to switch the places. So I'm going to write 5 in here and 1 in here and see if that is going to give me back my polynomial in standard form. 6x squared, 2x plus 15x, 17x, and 5 times 1 is 5. Now, as you can see in here, the constants in each factor would be the factors of the constant term in the polynomial, whereas the coefficients in each leading term, or in the x terms in each factor, will be factors of the leading coefficient of the polynomial. And the same idea will apply to polynomial expressions of higher degree. So in summary, we're going to say that when ax minus b is a factor of f of x, the values of a are the factors of the leading coefficient. And b are the factors of the constant term as it was before. That hasn't changed. To determine the factors of the polynomial in the form ax minus b, we must use all the possible factors of a and all of the leading coefficient a. Let me write the whole word actually. And all the factors of the constant term. So let's check and see how this is going to work for our polynomial here. So as you can see, here we have a polynomial where leading coefficient is different than 1. That tells us that this polynomial may have at most 3 factors, but it is possible for these factors, and all of them will have an x as a first term, but it is possible for these factors to have coefficients different than 1. And when it comes to the very last term in here, in each factor, it seems that we're going to have number 1 everywhere. So how do we work around this? So normally what we do is we start with identifying the leading coefficient. The leading coefficient here is 8. So therefore, we're going to say that the possible factors of 8 would be plus minus 1, plus minus 2, plus minus 4, and plus minus 8. The constant term in our case is 1. So the possible factors of b would be plus or minus 1. That's it. So based on the possible values of a and possible values of b, we are going to determine the possible values of b over a. And we're going to say that the possible values of b over a would be, we're going to start off with the first value of b and divide it by every term a. So we're going to say that would be 1 divided by plus minus 1, one again divided by plus minus 2, 1 again divided by plus minus 4, and lastly again we have 1 divided by plus minus 8. Now, because we have plus minus 1 only, what we're going to do here is write plus minus 1, and we're going to get the variety of terms right there. So all the terms, possible values of b over a. So we're going to say that b over a would be, remember, plus minus 1 divided by plus minus 1 is plus minus 1. Plus minus 1 divided by plus minus 2 is plus minus 1/2. Remember how we get these combinations. You can have 1 over 2, negative 1 over negative 2, positive 1 over negative 2 or negative 1 over positive 2. So then same with the next term, plus minus 1/4 plus minus 1/8. Now I'm going to start searching for the factors. I don't think we need this right now. It was just to explain what to expect at the end. So I'll probably erase it. So we are going to look into the possible values of b over a that will make the polynomial 0, so that we can figure out when the remainder would be 0. So f of 1 will be 8 times 1 power 3 minus 4 times 1 squared minus 2 times 1 plus 1. So 8 minus 4 is 4, minus 2 is 2, plus 1, 3. This is different than 0. Therefore, we're going to say x minus 1 is not a factor. Next, we're going to check f of negative 1. 8 times negative 1 power 3 minus 4 times negative 1 squared minus 2 times negative 1 plus 1. So that's negative 8. This is minus 4 plus 2 plus 1. That's negative 12 plus 3 or negative 9. That's different than 0, so therefore x plus 1 is not a factor. I was really hoping we get a factor at either 1 or negative 1 because they're easier to evaluate. Next, we're going to check f of 1 over 2. So we have 8, 1 over 2 to the power 3 minus 4 times 1 over 2 squared minus 2 times 1 over 2 plus 1. So this would be 1 over 8 times 8, 1. 1 over 4 times negative 4, that's minus 1. 1 over 2 times negative 2, that's negative 1, and then plus 1. That is 0. So therefore, we're going to say that x minus 1 over 2 is a factor. Now we're going to stop for a second here. Remember that when we say x minus 1 over 2 is a factor, we're basically forming an ax minus b factor, which will be 2x minus 1. Now, how do we get 2x minus 1? We multiply both terms by 2 because we're not allowed to have rational coefficients or rational constants in the factors of the polynomial. So, since we found our first factor, we're going to start dividing the polynomial. So we're going to have here coefficients 8, negative 4, negative 2, positive 1, and we'll be dividing here by 1 over 2. So this 1 over 2 is what we're going to use in our division, okay, for this particular factor. So we have negative 1 over 2 here. We'll bring 8 down. 8 times negative 1 over 2 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 8 times negative 1 over 2 is positive 4. Negative 2 plus 4 is 2. 2 times negative 1 over 2 is negative 1. Add, and then we get a remainder of 0. So as you can see in here, we got the quotient. Remember that we divided by half of the divisor, which means our quotient is twice as big as it should have been. So we are going to reduce by 2. And we're going to say that the first term will be obviously the x squared term, then the x, and then the constant. So the factors so far are 2x plus 1 multiplied by 8 over 2 is 4 x squared, 8 over 2 again 4, and then plus 1. So we have to continue factoring here. We have 2x plus 1. And as you can see here, we have a perfect square trinomial. The first term is perfect square, the last term is perfect square, and the middle term is double of 2x, which is the square root of this, and the square root of 1. So we're going to say that that would be 2x minus 1 squared. So f of x equals 2x plus 1, 2x minus 1, 2x minus 1. And voila, this would be the answer. Now, here is a summary of the rational zero theorem. And I wrote out the steps. Again, you can rewrite the steps in your own words and the best way you understand it. The next example, I encourage you to try on your own. I will continue with this example in the next video. As always, thank you for learning with me, and bye for now.